We're going to go through the Cooper-Jacob method for aquifer test analysis. This is from Octasolve. They're showing Jacob and for the Cooper-Jacob equation. This is also based on the W versus U equation that we talked about earlier, which has a infinite series solution for it. Turns out that for small radius and or large time, or just beyond early time, the first two terms of this series solution are good enough. So you get the drawdown equals Q over 4 pi t times the minus 0.5772 minus log of U, where U is R squared S, big S, over 4 big T, little t, transmissivity times time. And if I do that for two different times, and the drawdowns at those two different times, it looks like this. And if I do some simplification, I can change from a natural log to a base 10 log. I get that the change in drawdown, or the difference in drawdowns between two times, is 2.3 Q, the flow rate, over 4 pi times T, the transmissivity, times the log of T2 over T1. You notice that these other terms in here cancel out. If you look at this equation and you think about it, if you plot the drawdown on a linear scale versus time on a log scale, you'll actually, after early time, you'll get a straight line portion there. And if I look at the equation for that straight line, it turns out that the slope would be 2.3 Q over 4 pi t. And if I conveniently choose T2 over T1 equals 10, so if I go from 1,000 to 10,000, and if I look at the algebra on this, the log of T2 or T1 would just be the log of 10, which is 1. So we can get that T equals 2.3 Q over 4 pi delta S, where delta S would be the change in the drawdown over one log step in time. So we have 1,000 up to 10,000, and then that's our delta S, little s, for drawdown. Going back to solve for the big S, the storage coefficient. So from the slope, we get the T. Well, then we just extend that line down to where it hits the axis there, and we'll call that point T0. So from our equation, this would rearrange if S equals drawdown, 0 drawdown, that's the intercept down there, then that equation can be reduced and rearranged so that the S, the storativity, storage coefficient, is 2.25 T0 over R squared. 2.25 comes from minus 0.5772 and the pi in there. So we want for T0, we want the intercept where that straight line hits it. So we don't want the drawdown at time 0. We want the extension of that line. So here's an example here. So in this example, Q is 1.11 CFS, or 66.6 cubic feet per minute. R equals 100 feet. And just looking at my graph, the delta S here I had goes from a little below 10 to 20. And so on this one, I said that's about, my line's a little different on this one than the one I just drew up there, but pretty close to it, about 10.5 feet. I extend that straight line portion down here, and I hit a T0 of, and I got to read it off a log scale. I probably want more grid lines in there, like this one, 100, 200. Again, this one's a little bit different. I'm going to come up with a T0 of like 140 minutes there. So then I can calculate T equals 2.3 Q over 4 pi delta S, where again, S is the drawdown, big S is the storage coefficient, little s is the drawdown. So I have 2.3, and the units I'm going to do, since I have going to have time in minutes, so I'll do Q in 66.6 feet cubed per minute over 4 pi, and the delta S that I took from my equation was 10.5 feet. 10.5 feet. So the units are this one feet cancels out 2 of those there. So it's feet squared per minute. And I have it copied down here, 1.2, 1.16 feet squared per minute. Now that I have that number, I can go down into my S equation, plug it in there, and I have S equals 2.25. Transmissivity is 1.16 feet squared per minute, well, times the T0, which I picked off my graph, was 140 minutes, over R squared. R was 100 feet, and I square that. And hopefully what's when I did the right units the first time through. Feet squared over feet squared cancel out, minutes over minutes cancel out, so I do have a dimensionless, and this equals 0.0366. So it's 3.66 times 10 to the minus 2. Again, just like this is probably also from one of our underground storage tank sites, so that's kind of looking like it might be an unconfined aquifer. In the text, he also mentions that the Cooper-Jacob method can be used for drawdown versus radial distance. So if I go up to this equation and I keep the same time cancels out. But if I have different radiuses, then I have a similar equation for radius. And you also might see, so this is 0 drawdown up to 25 feet drawdown. You might see this plotted at 0 down to minus 25 feet. So have drawdown as negative. So then it's the same thing. It's just that instead of this going up, it goes down. So there's a couple different variations on it. And like I said a number of times now, we're trying to do just the most basic variation of 3 specific tests. Octasolve will have a lot of different variations on it. Looking at the Octasolve of the Cooper-Jacob method, it seems to imply you do it by a visual match, that they don't have an automatic one. Notice it also talks about you can do right up to the first recovery period. So in an aquifer test, you draw down and then you let it stop. The water comes back up. The next method we're going to do on a slug test is really on the recovery part of an aquifer test. Again, just there are a number of different variations on this. So that's the Cooper-Jacob method. There's a homework problem on this from the text, which should be fairly straightforward. If you have more questions, let me know.